getting the YouTube stream started because I keep forgetting to do that for these reading groups. I'm gonna undeafen the call in just a second. Everyone's doing good today. Okay. YouTube's up. Let's undeafen. Okay. Hello.
Hey, Don.
How's it going?
Good. How are you?
Doing pretty good. Phobos, how about you?
I'm doing well. Fembox, your mic is significantly lower than Don's.
Okay. So am I too quiet? Should I turn it up? I actually turned it down because I was watching back on the stream last week and it seemed like I was really loud and I didn't know I was that loud. I didn't mean to be that loud.
Yeah, right? Who's supposed to mix the audio on this thing?
We need an engineer, right?
Do you turn, so Phobos, on your end, do you turn the sliders up and down, like for me in Fembox, or?
No, I just kind of let it go.
Oh, okay, so I, like, usually when I get into Discord with people, like, I tend to turn them, like, up or down just on my end. I don't know if...
Yeah.
So are you saying I can, like, from my side, I can, like, tinker with you guys from my side?
I'm tinkering with you right now, Fembox.
If you right-click on each of our names, like I'm showing it on my stream right now, there's like a user volume slider.
Oh, okay.
Funny part is, it doesn't do anything for me. I'm adjusting... Whatever, I don't know. I chose to use Linux some years ago, and I've been paying for it ever since.
Oh, Discord Linux. Yeah, I wonder if that can do it. And hey, Joseph.
Look at that. I can turn you guys up and down. What do you know?
Yeah, I don't have an easy way to turn myself down. Me.
Am I at a reasonable volume? I'm assuming you're gonna twiddle the knob for me, but
Oh,
I never know.
You sound fine.
You're fine for me. Okay, I'm gonna have to change it back. Okay, I just turned down my mic to 75% in Discord. Does that make a difference?
Yep, you're quieter.
Okay. I hope that's better. But hey, Bloody Hoofs, how's it going?
Maybe we should all sing notes like a quartet or a what is it? When you have three people singing, is that a trio?
Yes.
I don't know.
It seems wrong. I don't know why, but it seems wrong. Tritet?
There has to be a word for it.
Tet.
I'm not sure. But I did make a fresh whiteboard for today's session. Do we have any requests for a problem to start with? So I can start like getting the screenshot if we need it.
I don't have a fresh whiteboard. I still see stuff.
You need to change to it in the upper left, that like triple bar view. Okay, yeah. Cool.
I'm here.
Awesome.
We can begin now.
Perfect. I'm gonna start going through ones that I took screenshots for in advance that I called out, but I'm happy to do anything. Number 9 is going to be an integral one. Phi from integration for a solid sphere. I'm going to bring that one up. Oh no, Discord is going to do this to me. Why does it do this? Yeah, I need to leave and rejoin the call. So sorry about this.
No worries.
Freaking Discord. Let's see if it decides to work now. Okay. I think I said 9. I'm gonna put in the upper left. And 2 more images, and we scale them up. Okay. So a solid sphere R has a solid sphere has radius R and uniform volume charge density rho. Find the potential of the center by evaluating the integral in equation 2.18.
Seems like you do that one with spherical shells, maybe. But you'd have to like figure out just the contribution of one shell and then integrate over that.
So we could do part B first then and use it for part A.
Oh, I didn't see that.
What is up with book authors and doing this? Hey, solve the whole problem. Hey, solve the first part of the problem. But I already... ... Unless there's an easier way. Do you know an easier way? Is there any symmetries that can be leveraged for part A, maybe?
I feel like I did a similar one, or maybe we just it as a group last week, but once you get, like, for the shell, once you actually get past the like border of the shell, like once you're inside, like phi doesn't change. Phi is constant, like inside, because the field is 0. I don't know why I'm drawing a phi when that doesn't really like say that much, but like all the work that you do is as if this thing was a point charge from the outside, and once you actually through, it doesn't change on the inside.
That makes sense, because the electric field's non-existent in there.
Yeah. I'm still okay. Yeah, I forget what shape it was, but we were breaking it up. Maybe it wasn't for these exact like shell. Like you look at just like a one like radial direction, I think, and you can break it up into rings and integrate over those rings. What problem was I doing? I was like that. This feels really familiar. I didn't do this exact problem before and I just forgot. Oh no, okay, it was a different one. It's similar to number 7. They actually... I said I have calculated the electric field due to a spherical shell.
I do remember that one.
Hey, Critical. Like I put in the title, but I'm doing math after this in about 2 hours. Potential. I don't know. Either way, though, we could we could probably take the same approach for both the solid sphere and the shell. One is like a ring, the other is a disc, I guess. Um, yeah, I do wonder if there's a way that we can like use the shell to help the solid. That would make sense.
If I were doing part A, I would just use regular spherical coordinates and just do a triple integral. But then, we got to do part B anyway. So at some point, we got to find out how to break off a shell.
Could we use Green's theorem or Stokes' theorem to like simplify what we do with that integration? So it's not a triple integral. I can't remember which one would apply, or if Green's theorem is just for 2 dimensions. But if you could do, if the conditions are satisfied and this integral is over 3-dimensional space inside of space, then shouldn't it be equivalent to some surface integral? But I think that depends on the nature of the function that we're working with. So it has to satisfy some condition. And I think that's being a conservative field.
I think you're right. I'm really shaky with Green's theorem and Stokes' theorem.
Same. I'm working up to it.
I do think in this like context of E&M, we are. I hope I'm not crisscrossing like different senses of the word conservative, but I feel like we're always working with conservative fields, at least for electric fields. In math in general, you're not always guaranteed that, but like they said, like the electric field is conservative, but I'm not confident in that. We might not have to go there though. Like I wonder if I guess if we did do the triple integral and spherical coordinates, what would the R be?
I think that would be the value ranging from 0 to big R. Little r. And then
Yeah, I didn't say which R I meant. Sorry. What? Please keep going.
And then I think the other 2 would be angles, but I think they would simplify to just being the surface area of a sphere.
Hmm. So like I'm not quite sure what goes there or what goes here or here for the balance of.
I think the one in the denominator is an R.
It is just that?
I think so. Because presumably R would range from 0 to big R as part of this integration.
You also need a factor of R squared sine of something.
Oh, good call. I forget how to do these change of coordinates.
Oh, just because it's a volume.
Yeah, the dv in Cartesian is dx dy dz, but in spherical it's something like R squared.
Wait, do you say big R squared wouldn't be smaller?
Oh, it's little R squared.
Okay, sorry if I misheard.
I don't think I said whether it was little or big. I should have said.
I don't know, question phi or theta for the sine.
I tried to do the physics convention where phi is like the polar coordinates, like if this is the x, y, and that's your point R. You have R and angle V, and then the theta would be the three-dimensional, like azimuth angle or whatever it's called.
The angle we need is the one coming off the z-axis.
Oh, really? Okay.
Yeah.
I guess that's theta then.
That's why I said sine of an angle, because I'm never sure which one is which somehow.
Yeah. Me neither.
Honestly, I don't even know in the Purcell book, which, I was looking through the Purcell book to try and find, like, well, okay, where does he define his spherical coordinate system? I actually couldn't find like a 3D picture of, the XYZ axes and then the R, phi, theta, with the angles. I couldn't find a picture in the book, and I thought, well, I'm not sure which angle he's using for the one in the XY plane and which one he's using to come off the Z-axis.
At the start of our studies, I cross-referenced it to Stewart calculuses to figure out which one was which. I've
Okay.
forgotten by now, but that was an effective method. Just look at it and you know by how it is. Just like trees and cars.
Yeah. It's all fine except when you want to go and back and use the list of formulas for the vector operators in Appendix F, and then you're like, oh, now wait a second, which one's phi and which one's theta here?
I wonder if the classes, when students take like an E&M class, if the professors have some keen tips to drop on the students, be like, look, I know you've seen this in Calc 3 class, but I've simplified this for you. You get a knowing wink from the professor and a mnemonic.
Hmm.
I remember one of the examples in chapter 1, they did explicitly say that V is like the two-dimensional one and theta comes off from the z-axis, but that's not necessarily like they have to do that every time. I feel like their emphasis is more just like being able to be arbitrary with what phi and theta are depending on the situation.
Oh.
Or I don't know, I feel like they just kind of like wing it. Depending on how they want to define things. Um, I'd be doing too much mental math at once right now, but oh, sine theta. I think I'm all good.
I think I agree as well. I think everything looked pretty good. And that presumably would be what the surface area of your sphere, maybe? Sphere.
Could one of you tell me how to zoom in on a part of the whiteboard in
oh,
Discord?
scroll. So like
I can zoom in and out, but only seems to be on the middle of the page. I can zoom out and see the top of the page, but if I try and zoom back in, I lose the active part of the.
it zooms to your cursor, I think.
Yeah, how
Use
do
a
I get?
touchpad?
Yes. Is that my mistake?
I mean, maybe not a mistake. Developers make some weird, inconsistent decisions about how things should behave when the device is different. So
Okay.
I have no idea.
I think Pen Center has had difficulty with the Discord board in his tablet. I don't know exactly what the details of that are, though. This does
Canon
feel
being
right.
lost. Where'd Fee go? So you integrated that so
phi.
it was a linear term and then plugged in the endpoints pi and 0 to cancel out a pi in the denominator. Is that accurate?
2 pi, but yeah.
Oh, I thought phi was 0 pi. Oh goodness.
Oh, yeah.
And I still agree. I agree.
Okay.
I follow.
Yeah, I mean, I don't know about this. I assume that the book has gotten this result in a different way somewhere else, so maybe we can verify this final. Actually, I just got 0. That's not good.
Yeah, that seems not right.
Okay.
Unless, I mean, maybe it is 0. Does that make sense from a
Just
physical?
check your signs on the final step. I mean, I don't think that's going to cancel out, right?
I
Check
think
your
it's
signs on the very final
the
step.
0.
Oh, there's a negative. I forgot. I'm losing track of my negatives. Okay. Okay, so it becomes a 2. Because there's the negative sign initially there that I forgot for the second one. Rho r squared over 2 epsilon. That seems like something. Gonna skim the chapter to see if they did this.
So what's this? This is the potential at the center of a solid sphere.
Right.
I feel like they did do something like that in the chapter. I remember them saying the work you had to do to bring a charge in from infinity was like 2/3 of the work was bringing it to the surface of the sphere, and then 1/3 of the work was getting it to the center, or something like that.
You're right. Potential due to a uniform sphere. Found it. Page 62. Well, 63. Okay, yeah, so they do it with the electric field as calculation they did. Oh. Huh. Oh, wait. Oh, we almost
Yeah,
get the right.
You got it. Equation 210, if you plug in r equals 0, little r equals 0, then we got it, right? Right at the center? I think it's right.
Potential at the center of the sphere is okay. Yeah,
And if you look at
you're
the
right.
graph
Okay.
just to the right, you'll see the sort of phi intercept of that graph is rho r squared over 2 epsilon naught. So you got it. I think it's right.
Nice.
It's right.
Yeah, it matches.
Integration.
Yeah, they make a point about the slope of phi is continuous because E of R. Never mind. That's not that related.
Nobody cares about continuity.
Okay. Nice job on that for A. For B, it's a shift between sigma and rho. I remember you can write it like a differential. It's like rho is equal to sigma dr or something. I don't know if it's really that important right now, but
Wait a second. Shouldn't that be d rho equals sigma dr? I guess I'm not
Oh,
following. What are you doing for part B?
I'm not quite sure.
Okay. You've
Um,
manifested a differential. Love it.
Yeah, that's the thing about going from like the three-dimensional density to the two-dimensional surface density. But I usually just swing it and don't think about that piece of it this hard. There's some kind of differential thing that you can do here that I don't remember.
Convinced. I'm convinced that's correct.
Okay. But I don't know if it's even like that relevant to this.
So couldn't we use the same triple integral from part A, but just change it to a double integral? And
Have a constant R factor?
yeah, fix the lowercase r to uppercase R. Yeah. And then replace the how do we do this? Somehow the rho becomes a sigma. Wait, sorry. No, it's not d rho, is it? It's dq. It's dq is sigma dr. Is that right? Because sigma is charge per area.
I think DQ would. I mean, I don't know if we need DQ because how the formula is, but I think DQ would be some kind of dependence with like well, there should be some kind of like angular dependence there. I feel like. Um. Rho is equal to like total charge Q over the volume of the sphere. So you could like rearrange that and get a differential if you cared. I don't know if it's even important, but
Yeah, so we don't want d rho because rho is constant, right? What we want is rho dv. So rho dv will equal sigma dA. So rho times a little change in volume would be sigma times a little change in area. And the dv is dr d phi d theta. And I think that dA is just d phi d theta. I think that works.
I feel like we need a big R factor in there though.
Yeah, I'm just trying to find a way to change the integral in A to sort of to use what the work we did in part A to get an answer in part B. I'm trying to cheat my way through it.
Yeah, same.
What's the problem number on this one?
I just got kicked out. I don't remember.
Oh wait, I have it on my other screen here. It's
once I get
number
back in.
2.9. 2.9.
It's right there on the thing. Sorry. I don't know why I blanked out.
Oh, my Discord just blinked out. I believe. Wait, maybe just the activity.
I wish I could work out how to use this whiteboard. Maybe if I turn it off and on, it will come up.
Well, this is interesting too, because they're asking in this case about the potential at a point on the surface.
Yeah, so I think we can.
Oh, interesting. Yeah.
I think I worked out what we need. We need sigma equals rho times dr. That's what we needed. Sigma equals rho times dr. Do you guys agree that that would make sense? So The surface density is the volume density times the little change in radius.
Yeah, dimensionally that makes sense.
Yeah, so we can use that and plug that into the integrand from part A. And that'll get rid of one of our 3 variables of integration, right? And then we replace the little r's with capital R's. That's my gut feeling anyway, that it might work.
The R squared, the big R squared on top, I definitely agree with. The R on the bottom, I'm still thinking about. I mean, maybe we can just go through with it and see. We should be able to make some kind of realization with comparing the answer from the other one. Or with the example problem in the book, too.
Did they do a spherical shell in the book?
It should be the same as the, like, the outside calculation they did, I would imagine. Because they got the fee for the outside and I think added to the fee for the inside or something. Hmm. No. Pi's cancel. 2. Beta d theta. Just be another factor of 2. Sigma r over just epsilon naught?
What did we get for part A?
Rho r squared over 2 epsilon naught. So, this looks almost similar. So I was thinking it should be similar to the, or it should be basically the same as the phi outside calculation, except we'll have a sigma instead of a rho. And if you take small r equal to big R, our answer nearly matches, but they have a 3 in the denominator that we don't have. No, wait, we have just r, not r squared. No, this is just not right. Hey, it's G1.
I don't think it'll match that because that was still based on the solid sphere.
I guess I was kind of... Is the field for a shell the same as the field of a solid sphere if you're outside? That's what I was assuming. Maybe that's bad. I have to look back at chapter 1. There might be a different... Yeah, it might just be supposed to get a different thing. Okay, maybe I'm just crazy when it comes to that. Are these related in some way, though? When written in terms of the total charge involved, how do the two above results compare? I guess it's gonna be helpful to rewrite them in terms of the total charge. So rho is equal to Q over, or yeah, Q over 4 pi. So I'm off to the right of our work for part A, just switching out rho.
Yeah, let's see what this gives us.
Oh, big R cubed. Two epsilon. Q 8 pi epsilon naught R. That's my claim. I think I did that fraction math right. And then sigma is Q over 4 pi R squared. Big R squared again. Ugh. This notation, I don't like either with small r and big R. It makes sense why we use it, but it's cause for confusion. Q over 4 pi epsilon naught R, which isn't that just the default potential? Which I think might make sense. Or like the potential for like a point charge. Yeah. Which, maybe, should the solid sphere be the potential for a point charge? No, okay, I think it makes sense that the shell is like a point charge because of that idea that you're doing zero work inside of the shell, and you wouldn't go inside of a point charge either. Whereas the field actually changes inside of a solid sphere, and so the work you're doing changes. Hey, AS Gaming Bros. 3Q over 8.
But in this case, for part B, we have a spherical shell, not a solid one. Right.
Right.
Okay.
And I'm thinking that makes sense because of that. It is a shell, or I'm thinking that like it matches a point charge because it's a shell. I'm hoping at least.
Yeah, I have no clue.
So for the solid, we had 3 over 2. So the ratio is 3 over 2, 3 over 2, right? The solid is 3 over 2 times as much as the shell.
That's the same as the ratio of the work done to get to the outside of the sphere versus going all the way to the center of the solid sphere from the one example.
Oh, really? Was it?
I think the ratio is 3 over 2.
Huh.
I won't check the answer in the back of the book on this one, unless anyone has any objections.
No objections.
Okay.
I'm gonna look at that example again really quickly that you just mentioned.
Actually, yeah, we can. Yeah, I found it. The potential at the center of the solid sphere is 3 over 2 times the value at the surface. So that gives me some confidence that we actually did this right.
Yeah, it sounds convincing.
What did we say this number was?
9.
9. Okay. Oops. But the answer for the 4-star problem is like 2 pages. Ugh. Okay. Oh, they do a shortcut to avoid a triple integral, but it ends up being the same thing. We just set it up different. Big R squared rho over 2 epsilon naught, that matches. Sigma big R over just epsilon naught for part B. And then for part C, okay, yeah, they point out that 3/2 ratio. Because it's consistent with the result from the second example in section 2.2. Okay. I think we nailed it.
What did they do
Nice.
for part B?
All points, oh, they break it up into rings, like that one problem we were doing before, I think. I don't think it was during an actual reading group, but oh gosh. Okay, they have some weird triangle stuff going on, but
What?
I think it's more or less the same idea. All rings are at a distance 2r sine theta over 2 from the pole. This will take a lot of geometry for me to actually follow this argument.
See, that makes me wonder if my little idea about just changing sigma to rho and writing the R's as big R's was valid. We did part A a hard way, they did it an easy way, and then they did part B a hard way, and we did it an easy way.
Definitely got the right result. Maybe it's a little more like a... We did a little more like intuition-y of what it should look like rather than actually showing it.
I like using the shortcuts based on intuition, but you know, you gotta be careful.
Yeah. Oh, what? This is a stupid integral they end up with. They have sine theta over sine theta over 2. Oh, that just becomes cosine theta over 2. Never mind. I probably wouldn't have set all this up on my own, or without like, I feel like I did something terribly wrong if I ended up with theta over 2.
Yeah, that throw me off as well.
I might start looking for another question though.
Yeah.
I have one called Disks and Dipoles, a 2-star. Oh, that's a 3-star. I don't know if we want to do a 3-star. Ooh. Going... Oh, is this going to be... Let me look at the formulas. I want to see... Oh god. Sorry, I just clicked on the wrong thing and I have sound playing in my head. Well, also my headphones, but... I have a problem where they give us phi and they want us to find the field. Okay, yeah. Number 20. I'm going to bring it up in the whiteboard as well. And Discord is being mean to me. 1 second. Gotta leave him and join. I don't know why this image uploading thing doesn't want to work. Okay. Number 20 is up just below where we started for part B of the last one. Here they give us the equation for phi, and I assume we're going to use the formula. I'll just write it out here. E equals the negative gradient of phi. Oh, this is just one-dimensional, so the gradient won't be as crazy. Field and charge distribution. Oh, we also need the charge distribution. What's the formula for that? With the Laplacian of phi is equal to minus rho over epsilon naught. Okay. Well, I can tell you for the first one, my guess is 0 and 0 for each of them.
Yep.
Let me like do it so it's completely off the image. And then we have two other parts for x between 0 and L. I guess we can start with that one. I don't know why. I guess if I wrote x hat for the first one, I'll keep writing x hat for this. Well, it'll be 2 rho naught x over 2 epsilon naught x hat. And we can cancel the 2's. I don't know why we're using rho naught now. And how do we get the Laplacian? Is that just the second derivative?
Yeah.
Okay. So rho is minus epsilon naught times the Laplacian of phi, which is just the derivative of the thing we just got. And I got kicked out of the whiteboard. Isn't that great? This thing, it only half works, but it's convenient. Is the Laplacian? It's a scalar. Okay.
Yes.
Um, so the x just goes away to 1. Did we get just rho naught? Because the epsilon cancels, the x goes to 1, and the negatives cancel. Okay, I'm saying it's rho naught.
Oh, that's funny. I can see my cursor on your screen, but not on my screen.
Oh, if you were to leave and rejoin the activity, you can get it back. But after some amount of time, it just like the cursors freeze. I'm not quite sure why.
Maybe that's why I haven't never been able to zoom in on the right part of the screen. I don't know.
Yeah, if it stops working, it doesn't hurt to like just leave the activity and rejoin. But it's not a big deal. And just leave it.
Do I have to leave the whole won't
No,
come
you,
back?
it's like I'm hovering over on the stream. Just leave like the hang up button becomes a leave activity.
Oh,
Um, and then you just go back out to the call, and then there'll be a button to like rejoin the whiteboard.
okay. I'm gonna try it.
It looks like the third one, it's a constant potential. So I think we're getting 0 field and 0 density. Because there's no X dependence. We'd have to sketch these as well.
So let's see, what would that mean? So we don't have any charge outside of the interval 0 through L. And from 0 to L, the charge is constant, is it? The density, charge density is constant.
So I guess we just have a one-dimensional line with constant charge density. It starts at 0 and ends at L. Rho naught is the charge, and then I guess our one-dimensional field lines scale linearly. So off to the right, X is positive, and we get a vector pointing left because of that negative sign. I don't know if this is... I'm probably not scaling this quite linearly, but the arrows should be getting just a little bigger each time. I guess it depends on row, but are we given the sign of row? No, I guess not. Okay.
So you're saying the field points to the right if we're left of 0, and the field points to the left if we're right of L.
Right.
What about in between? If we're in between, it would still be pointing left?
Oh, wait. I have this backwards. Yeah, I was using like that result there for the field. That's only valid for inside, for between 0 less than X less than L. The field is... I said the field is 0 outside of here.
That's right, we did say the field was 0 outside.
How is this possible? This is just giving us some arbitrary thing. So if this math was right, I guess it would always be x is positive. So at least for this interval, it'd be pointing towards the origin? That feels very...
And it's pointing. And when x is 0, it's 0.
Right.
So it's actually pointing stronger the further you get away from the origin.
Yeah, I guess I should have drawn that so they're a bit longer on the right. This feels like I have no idea how the situation would actually happen, but I don't know how else to interpret these equations.
I think I missed a lot of this question, but which question number is this again?
20.
20. Because it could be if you have a potential that increases as you get further away, the points are attracted to each other.
Increases. Let's get further away. Yeah, potential is increasing. They're attracted to each other.
So they want to go towards each other. So taking it further away would add potential energy to the system.
Maybe.
You know, I just had a thought too. I mean, it says it's a one-dimensional charge distribution, but that doesn't mean we have to restrict our field to be one-dimensional, does it? I mean, shouldn't we still be considering points off of the x-axis to calculate field and the...
Oh. Well, that would make sense, but wouldn't our gradient for the y-axis be 0? Like, there should be some kind of field there if this was two-dimensional, but I don't see how we mathematically get that field in the y direction. Yeah, this is like the case of an infinitely long wire, or I guess this is a finite wire, but it's still like that.
Nope, I don't think I get it. I was gonna say maybe what we're dealing with is not just I was gonna say maybe we're dealing with like an infinite plane that exists from x equals 0 to x equals L. And it's like a two-dimensional plane, but it says in the question it's one-dimensional, doesn't it?
Yeah.
So I guess what I'm thinking is y could be any number, but we'd get sort of the same answers no matter what y was. In which case the field that you sketched would be existing in a infinite plane.
Yeah, I
Kinda
think
like
some magical world.
Yeah, kind of like there's a wall perpendicular to your axis there that goes through the points 0 and L. And it's like heat being lost through the wall to the outside or something.
That's kind of how I was imagining it too, like something that's like stopping this charge from actually making a field further outside. Because this is weird, because we don't usually talk about going parallel to the object. Usually we talk about the field perpendicular to the plane or perpendicular to the line. But even then, like, for those situations, like, going parallel wouldn't necessarily scale, like, with x squared. So I think it's just some make-believe scenario.
Yeah, maybe.
I kind of want to check the answer on this one as well. Oh,
Maybe when they say it's a one-dimensional charge distribution, maybe they just mean the way the charge is distributed only depends on one variable, right? It doesn't mean that the charge has to exist along a straight line. I'm starting to think this infinite plane idea might be worth thinking about.
so I've only looked at the first paragraph of the answer, but they're just saying that e sub y equals e sub z equals 0. Wait, in the region 0 is less than x less than L, and e sub 0 in the other two regions. I think they don't seem to be going three-dimensional at all here in the answer key. They do give some interesting looking graphs. Obtain the charge distribution. Rho of x equals minus rho. Oh. Why is it? Surely it's positive rho. Wait, note that e sub x is continuous at x equals 0, but not at x equals L. This implies there must be a surface charge density on the plane at x equals L. Okay, so maybe they are getting a little three-dimensional. Or they're talking about the plane case as well. Oh, it is positive. Wait, I said it was positive, bro. No, negative. There's supposed to be a minus sign in the answer that I put for rho. Because I forgot that the formula for E had a negative sign tacked onto it that I brought down also. Hmm. Oh, so what they're saying with the plane stuff is um oh, you're out, hobos? Okay. Well, thank you for being here for as long as you could. Hope you get some rest.
See ya.
I think this idea of the plane is that shoot, I don't know how complex I want to get with the drawing here. There's a discontinuity in the field. So on the left side, the field kind of fades off to 0, and then as you around the, okay, maybe I should rephrase this. If you approach the origin from the right, the field drops off to 0. If you approach the origin from the left, the field is always 0 anyway, so there's no discontinuity. But around L, the field is pretty strong and then suddenly drops off to 0 on the other side of L, which implies there's some kind of plane parallel to the YZ axes because of that discontinuity. I think is what the answer key is saying.
What's that green plane you just drew?
It's like if the x-axis is the black axis, this is some plane that's parallel to the YZ plane.
Okay.
I mean, that's not actually parallel to. Sorry, what?
And I see what you're saying. So just on the right-hand side of that green plane, the E would be 0, but right on the left-hand side of it, it's positive. It's not 0.
Right.
So there's a discontinuity, but what is that? What's the significance of it?
That's a good question.
Does it mean there's another? Does it mean there's a charge? That's a charged surface or something?
Yeah, they're saying there's a surface charge density there.
Oh.
I don't know why there wouldn't be anything on the right side. But like in chapter 1, when they calculated the field due to an infinite sheet, there's also that discontinuity that happens right on that sheet. And I think they're making that same argument here.
Yeah, I remember that right at the end of chapter 1, right? They were talking about that.
Yeah.
That was due to like a sheet. That was due to like an infinite sheet of charge or something, wasn't it?
Right. This doesn't contradict the volume densities we just found because those row values have nothing to say about the row values at the boundaries between the regions.
Oh.
Where are these defined? Oh, yeah, this function is not defined right at 0 or right at L. Okay. The initial phi of x function. Which seems kind of cheap, but okay.
Yeah, I guess I'll buy that. So when we did our gradient and when we did our Laplacian, it didn't really tell us what was happening right at 0 and right at L, right?
Yeah.
Okay. All right. I guess that's like, in calculus where you're trying to find critical points of your bounded function and you have to like do the calculus, but then you got to pay attention to the endpoints as well. That makes sense.
I guess so, yeah. To determine the surface density sigma on the plane at x equals L. Wow, they took this way deeper than I thought.
Well, I was thinking for a 2-star question, there's probably something else going on here.
That's fair, yeah. The field across the plane, the field just to the left. Oh, they're gonna use that average formula, I bet. Gauss's law tells us the change in the field. Oh, never mind. They're doing a simpler thing, I think. Oh yeah, this has a net flux through it, so you can just use that with Gauss's law if you make a solid there. Sigma is rho, not L. This is so weird. They only give us that there's charge. I guess they also give us that there's no charge off to the right, but like it feels weird that we went from this one-dimensional string of charge, and we can figure all this stuff out about there must be some kind of infinite plane also here. The external field, so like outside of this one-dimensional string, is the same as the field from two oppositely charged sheets that are just spread apart a little bit. That makes sense. Where it'd be zero outside of those sheets, and I mean, I have to work out if it's like why it's scaling linearly inside them. Actually, well, maybe that part inside will be different. There, we'll talk about the external part. Figure 12.44a shows a view of the slab and sheet. Oh, that's it right there. Okay, that's not that helpful to me, but it's there. E sub x and rho sub x are shown. Oh, and phi of x are shown in the following ones. Okay. As mentioned above, the first derivative of phi, which is that the field is not well defined at r equals L. The second derivative, which is related to the density, is not well defined at x equals 0 and is infinite at x equals L. Okay, I guess maybe my remaining thing that I'm not sure of why is right at x equals L, they figure that rho is infinite and e sub x is 0. And I'm not sure why still. If you tried to calculate the Laplacian at x equals 0 and x equals L, you would obtain results that are respectively undefined and infinite. Hey, Aspirin. how to integrate the root of cotangent of x. That's gonna be some crazy integral that I don't would be a very long one. Sorry, what 10 bucks?
I'm wondering why they are saying that the Laplacian is infinite.
Yeah, like if we don't have any defined function at these points, then how do we figure that out?
When you drew the graph, right? I was of the charge density with the green color. I was thinking, okay, it's zero below zero. It's rho zero from 0 to L, and then it's 0 above L. But I wasn't considering right at the points 0 and L. You know, it just felt like it was just a little jump discontinuity at those 2 points.
Yeah.
Okay, so you're saying, so it goes back to what you told me a minute ago. At the point 0, the electric field is continuous, right? The vector E is continuous as we go through 0, but the vector E is not continuous as we go through L. So
Right.
they're saying because of that, it means we have some kind of point charge located at the point L. So if there's a point charge located at L, maybe that's why the Laplacian is infinite, right? If you're at a point source, maybe the Laplacian of the field would go to infinity, like at the point. It's like a singularity or something. Maybe that's why they could say that.
Yeah, that might be it. Aspirin, I'm gonna be doing math in maybe 40 minutes or so, but I still don't. I'm not gonna know the answer to your question. I don't think.
Square root of cotangent. Oh, come on.
Yeah, it's gonna be a very long and difficult integral. I've seen the for root tangent x, and I assume it's gonna be similar. Okay, I think I just need to come back to this with like a fresh mind later for this answer for 20.
Okay, it's interesting that we can. That's kind of cool though, that question, because I guess what they're showing us is that if you know the potential function, I think it's kind of like saying, it's like knowing the gene map of the whole. It's like you can reverse engineer and build everything from it, right?
Yeah,
Isn't that funny? It's like it didn't feel like we were going to get something so crazy with that problem.
I didn't think so either. um,
It's kind of like, you know what it's kind of like? It's kind of like thinking if you knew the gravitational field in an entire massive region of the universe, you could like use it to work out where all the planets were, right? Like and how big they were and
oh, probably yeah.
something. Yeah. You could find out where the black holes were, right? That's probably what it is. It's like there was black hole here because, the field the field has a discontinuity and like, so there's a black hole.
Yeah, that probably is the same thing. You're right. Huh. Okay, maybe I'll bring up 22. Talks about discontinuities in E and Phi, so it feels relevant. What kind of charge distribution yields a discontinuous electric field? I guess these are a little more like discussion than calculation. I think any type of like surface charge distributions are going to do that. I can't think of one that have a continuous field anyway.
Yeah, that feels like just what we were just talking about.
Yeah. Is there maybe a three-dimensional one that could have a discontinuity as well, though?
Hmm. Okay, what about a point charge? Does that work or no?
Um, ooh, that's a good question. Because it's not defined for zero radius.
I don't know if that counts as a discontinuity.
Yeah, because I'm kind of getting into like, I remember during Zach's real analysis class, I tried to use 1 over x as an example of a discontinuous function. And then it was pointed out that it is continuous, just only continuous where it's defined, which is everywhere but 0. I
Okay,
have like a
okay,
similar vibe about this.
yeah.
I am wondering like, so this is for a discontinuous electric field. Does a solid sphere have a discontinuity from the outside to the inside, or do they happen to meet? Maybe I'll go back to chapter 1 and look.
Yeah, that example we were looking at. That example we were looking at where we were talking about the 3-to-2 ratio or whatever it was, that was they graphed it and it met. It met very nicely.
Was it phi that met or e?
Oh, that was phi. You're right. That was phi I'm thinking of.
Oh, I think e also meets though. I think I just found the chapter 1. They have a little graph here for inside versus outside, and while they are different functions, they do happen to meet right at the radius of the sphere.
Oh yeah. Actually, this is beautiful. I'm glad you brought this up. Now that graph right there, right? That's the electric field.
Right.
We take the derivative of that graph. Is it the
Oh.
derivative or the integral? It's the integral I want, isn't it? Yeah, if you integrate this graph as you move from left to right, the graph you get is the graph of the electric potential that we looked at from the chapter 2 example.
Oh.
Yeah.
I want to get these like side by side. Let me get a screenshot.
Yeah, that's what I did when I was reading the book. I got them side by side.
And then for phi, that was in the answer key.
wasn't any answer key. It was, wait a sec, let me find a page.
Oh, it wasn't?
No, it was,
Oh, I was thinking of the one-dimensional thing. Oh,
here it is, page 63.
cool. Hey, SPQ. Okay, I got my screenshot. Let me get it in the whiteboard.
Yeah, they even made the graphs about the same size. So if you kind of put them, instead of next to each other, left to right, you can put them one above the other one, and you can kind of see how the integral of the E becomes the phi.
The integral of E. Where's this integral, I guess, starting from?
It's negative integral, isn't it? Right, because we're increasing. No.
Yeah, I'm getting a little tripped up on that. It's maybe the integral from R to X?
Yeah, it's the negative integral. Phi is the negative gradient. I got it backwards.
Because yeah, it is E dot ds equals phi. Remember that. The negative. I guess the bounds I'm not sure about. I should, instead of x, I should say small r.
Yeah, E is negative gradient of phi, right? So, okay, so, yeah, so the negative derivative of the bottom function gives us the value of the top function, right? Yeah, that's working. So if you look at the graph for the potential, it initially has a slope of 0, right? Right at
oh, true, yeah.
And that's why the electric field is 0 at that point. And then the maximum rate of decrease of potential occurs at the dotted line, right? Which is the radius of the sphere. And that's the maximum decrease in potential at that point, right? And that's the maximum, that's the highest value of the electric field. So, so I'm saying that the slope of the bottom, the negative of the slope of the bottom graph is the value of the top graph.
Yeah, that's neat. Because yeah, that's the steepest tangent we get. Well, if I can actually draw. That's the steepest tangent we get right there, and it coincides right with like the apex up there.
Yeah.
I like that. Hey, Spetri. Germany won against Denmark? Oh, nice. How many more, like, rounds are there? Like, how close is Germany to, like, winning it? Okay, that's a nice little, like, point to make, I guess, for why this is continuous for the solid sphere. We often, they're in quarterfinals? Okay, nice. I'm kind of wondering about, like, something like a hemisphere. We've only ever really considered kind of the nice case of, like, coming right out of the center axis. But is there going to be some kind of weird behavior around the rim? Or is there, okay, like, could we fill in the vectors, like, transitioning from going straight up to down and to the right? I feel like it would transition. It wouldn't just jump. Because, right, if we just consider just that outer ring, I think that would be making a field in all directions outside. What else have we considered? I wonder if it's generally true, like for if you took like a cylinder, if the field would be continuous right at the surface. I feel like it would be, but I don't know why. And I guess we can also like discontinuous potential. Limit of a charge distribution. That little parenthetical is kind of intriguing there.
The charge distribution means we have some kind of a density function, right? Like a volume charge density or a surface charge density.
Uh,
What does
I
it
guess
mean
so.
to take the limit of that? It'd be kind of like if you had, I don't know, a disk. So let's say we had a disk, a solid disk of charge that was uniformly distributed over the disk, the surface, and then what would be the limit? Like pushing it all to the outside to make it a ring, or pushing it all to the center and make it a point? Is that what they mean by the limit?
I'm wondering about like I guess I'm going back to this like integral thing we were thinking about. And maybe they're talking about like an asymptote, like we have a vertical asymptote. I guess the field wouldn't be defined there either. I don't know if that's really what I mean by a limit though. I was hoping to use some argument with like finding a corner in the function, but I don't think we're going the right direction with the derivatives because like the e has a corner that you can't differentiate at for that solid sphere, but we're integrating it anyway, so that doesn't matter. I guess if phi had a corner, we would be in business. Um, which I mean, I guess there's no reason as like 20 was a pretty hypothetical situation. Like we just say he has a corner. Differentiable. I don't know if that's a little bit too general though. Oh wait, I'm doing this wrong. That's for part A. Is it possible to a function to exist continuously but not have an integral? Guess I'm trying to think of a part B. I don't think it is, though.
That sounds like a real analysis question.
It does. I'm trying to think of how, like, I'm trying to think of, like, if one answer works for A but not also for B. And I think it's just that, like, if for a function to be differential, it has to be both continuous and smooth. But I think for an integral to exist, it just has to be continuous. So we could name something with a continuous phi, but a discontinuous electric field. But we can't name a continuous electric field and a discontinuous phi, I think is what I'm trying to say. I'll try and like type that out too. E. I might be getting too mathy for the physics question here.
Yeah, I like that idea.
It kind of intrigues me. Yeah. Integrability. Do you need it to be continuous to be integrable? I'm thinking of like a Leibniz integral, or I don't know. Maybe that's getting way too deep for physics. I don't know if this last statement is even true. That it requires continuity, but
You're saying continuous E with discontinuous phi, right? Is that right?
oops, you're right.
So that nice little picture they had in the chapter that sort of tied together the E and the phi and the
Oh, that flow chart, right? Or the circular thing, yeah.
So if we want to get from potential to electric field, we use gradient, right? That's how we get from potential to electric field. We take the gradient. Whereas if we want to get from the electric field back to the potential, what do? We integrate, right?
Yeah. I just found the formula now. Or I just found that like chart now. Because phi is negative E dot ds. So yeah, we would integrate the field to get phi.
Negative integral E dot ds. So let's see, part A of this question, what kind of charge distribution yields a discontinuous electric field? So does that mean we're trying to look at the top left arrow in this picture?
Let me bring it back. The left side is rho, the right side, I think we want the two that are in the upper right. So we haven't talked about rho at all, I don't think, for 22.
Part part A talked about the field and part B talked about the potential, and they both talked about charge distribution. Isn't charge distribution kind of tied in with the rho?
Yeah, I mean, charge distribution is rho. Like, maybe there's something we can say with that too. I guess I've been thinking about this in terms of what kind of shape we can make. At least that's what I was doing at first with like a solid sphere and all that, which I was basically thinking about the charge density. Maybe there's a more like math way to make a discontinuous charge density and what would be continuous or not.
Yeah. So what kind of density function can we have such that E would come out being discontinuous? You were saying a surface charge.
I guess I notice in both cases, if you want to go from rho to E or phi, you integrate rho in a volume integral. For E, you divide by r squared, but for phi, you divide by just r, which seems significant. Like, could we name some rho with a factor of just r? And get a cancellation in one but not the other? So if I took rho equals to 1 over... If I want a sphere that gets denser the farther away we are, just have something to play around with. Well, ooh, it wouldn't be 1 over r, we just r. Linear charge sphere with charge density scales linearly r. E of this thing, according to that chart, will be 1 over 4 pi epsilon naught rho over r dv with just a volume there, but the field rho over r squared r hat dv, you would have a factor of 1 over r for that integral. So I'm wondering if that can cause some kind of kink in the cause a kink in E but not in phi. Is that what I was saying before though?
Maybe. You mean
Okay, yeah,
what
this
you
is the
were
same thing I was
saying?
saying with the like conjecture that I typed out.
Yeah.
So like the first integral would always exist for a finite volume. The second one may or may not always exist. I think this is more or less the same thing that I was guessing up ahead or up above. Hmm. Is this their idea with the limit of a charge distribution, though? Oh, they're talking about maybe going from discrete to continuous charge distribution?
That's what it sounds like to me. And like the limit of a charge distribution, it's right. It sounds like you're going from something continuous, like spread, like painting it out over a surface, to taking it all and squishing it into a point, maybe.
Yeah, maybe.
If we get a point, if we have any kind of a point charge, we obviously have infinite potential right at that point, right? Because if you're dividing by zero. But like you said a minute ago, does that really count as a discontinuity? Because it's not even, you could just say, well, we're just not going to define it at that point. It's right. So
Yeah.
instead of an asymptotic discontinuity, we want something maybe that has a jump discontinuity, right? Like in the last example we just did, it went from something finite to something else finite that was a jump.
Fair, yeah.
Well, how did that work anyway? How did they define that thing? They had something like, it was like a parabola, wasn't it? It was like they had x squared.
Yeah, they had it went from a parabola to constant. So to be fair, it actually was still continuous, but there was that corner there for number 20.
Yeah.
But we could absolutely,
continuous.
like, as long as we name arbitrary functions, we can name a jump discontinuity for sure. Sorry, what?
No, I was just agreeing with what you said. So in number 20, the potential function was continuous, but it had a cusp, right? It had a corner at that point.
Right.
So the fact that it had a sharp corner meant that when we took the gradient right there, we had a jump discontinuity in the gradient. And therefore we had a jump discontinuity in the electric field.
Agree, yeah.
Okay, well, I mean, I understand that mathematically, but I wasn't even really sure I understood in number 20, like what that. So
I feel the
we
same.
we were trying to reverse engineer it. And then the answers, they said, okay, what that means is that we have some kind of a surface charge on that plane, right? Hmm.
I think we'll let's look at the answer on this one now.
I'm going to guess that part B is impossible. I'm going to guess the
Maybe.
potential function can't be discontinuous.
Oh, good. I see some graphs going on in the explanation here. Just make this bigger. Okay. Okay, so a surface charge gives a discontinuity in the field. If E sub x looks like the curve shown in figure 12.46 up there, Rho is the derivative of the field. Wasn't this thing there's going to be discontinuity in rho, surely? Delta E over B. If we let B approach 0 and rho approach infinity, while keeping rho B finite.
Oh man.
This is a little heavy.
Sounds like the problem Penn Center was doing on his stream today. Sorry, Zach. Sounds like this.
Oh, I saw that with the distribution.
Yeah.
Yeah. But I guess that's all just discussion on a surface charge density, which we at least got.
Well, you got it. I don't think I was going to come up with it.
I mean, I remember them giving it, like, they talked about the example decent bit in chapter 1, just made me think of it. But like taking the average of the field on one side and the field on the other side at some point.
Yeah. Yeah.
Okay, part B. Two sheets with opposite sign charge density separated by distance s. So two sheets. Okay. Vector field between them is sigma over epsilon naught. Is that a Gauss's law thing?
Yeah, I think so. It sounds like doesn't it sound like a parallel plate capacitor?
I think so. I it's been so long since I've learned about those, but I think that's what a capacitor is.
I think that's coming up in the next chapter, maybe.
Okay. I guess they're only making the Gauss's law solid on one of the sheets. If they're getting sigma over epsilon naught. Oh, right, because yeah, I can make it over both sheets, there wouldn't be any flux. Okay. Potential difference is ES, sure. They do a similar S approaches 0. The distance between the sheets gets smaller as their charge gets bigger. We have a finite change in phi over 0 distance. Really? Which is a discontinuity. Do we?
So what did they do? They said that you get the plates of the capacitor infinitely close together. And then you get infinite voltage between them.
Maybe they're saying as the two sheets are infinitesimally close together, you have the area between them with some finite non-zero phi, and the area outside has 0 phi, but it's nearly 0. So they're trying to engineer a jump discontinuity with that.
Okay.
That's my best guess for that first paragraph. This limiting scenario is much less physical than the one in part A. Okay, I'm glad we're not supposed to have come up with a very physical answer. It's like realistic. Situations with finite sigma s and infinite sigma actually require an infinite amount of charge in any finite patch of area. Okay. There's a little footnote down here about it too. Oh, okay. I don't know if that's that important. Discontinuity fees consideration rho is the Laplacian of phi. (12.47a). And then b is the first derivative for this example phi. Oh. And d phi dx would be our field, more like, or an analog for the field. And the second derivative of phi here, wow, so they name a function that only gets a jump discontinuity after the second derivative. But that's still discontinuity in rho. I guess I'm going to make the same limit argument or something.
This problem really feels like it's going along well with the last problem we did.
Yeah. So I'm gonna read this, like, I guess, last paragraph here. Relation. Okay, yeah, these feel a lot deeper than I'm gonna quickly understand, I think.
Oh boy, I've been trying to study this stuff, and I'll tell you, every week it's like another bout of humiliation.
Yeah.
It really puts me in my place.
Yeah. I remember hearing, like, physics and depression saying that E&M is so tricky that even the professors get tricked from simple questions very, like, easily.
Yeah, he did say that. Yep.
I don't know, these questions are definitely fun. I just, like, they require a lot of thinking.
Yeah, they're fun. It's beautiful stuff.
Yeah. I might go.
I feel like so 3 problems today. The first one I feel like we did pretty well, but the second 2, I'll tell you, I felt like.
Oh, true.
Yeah.
Yeah, the first one we can really, like, write our names on proudly, I guess. I don't know what the right word is, but did a good job on that one. The second 2, I think we scratched the surface, but that's all we can say. Hey, hard
I
luck.
said last week, I need some 0.5 star problems.
Yeah. I want to take the limit of stars as they approach 0.
Yeah. Pretty good.
Yeah, I might switch back just into normal like math mode now. We're just about at the 2-hour mark.
All right.
Thanks for being
I'll
here.
bid you farewell. Thanks for having me.
Yep. I'll see you around. Oh, why? Okay, there. Here I am. Thanks again for being there, Fembox, and to Phobos. Switch back into math. Let's get some music going. Just give me a second to switch over my title and category. Both on Twitch and on YouTube. And song's kind of a banger. Wow. Okay. Oh. I feel like I'm forgetting something. Oh yeah, let me adjust my Discord. Okay. Yeah, critical. It's math time. Math and music very nice after being brutalized by Purcell. Yeah. Seriously. If you got a question, critical, go ahead and post it. I forgot to post our notes. Let me go grab that whiteboard quick. Sounds good, critical. Notes for today's group. Wish, it's been a minute. It's going good. How about you? Had a Nobel Prize in physics and was going to write an E&M text. Probably make all the problems hard too. Yeah, you really earned it at that point. Wonderful. That's great to hear. Trying to think. I feel like the last I heard from you, you were maybe about to do some finals. Maybe I'm misremembering though. Either way, I'm glad to hear you're doing well. Switch your degree from math to mechanical engineering. Oh, hey, as long as you're enjoying it more. Get my mic put up. I don't need that anymore. Just out of curiosity, since someone did ask about it during the physics, what is the integral of the square root of cotangent of x? Probably something insane. You love math, but you can't do research? Fair, fair. Yeah, I'm not doing that. A quarter root? Wait. This is, okay, just to be clear, this is arctangent of the fourth root of the negative cotangent squared of x? How does that work? Isn't this a negative number that you're taking a quarter root of? These are all quarter roots of a negative number. You know, so someone asked this question just before this when I was doing physics. And I was like, I'm pretty sure that's something insane. Yeah, it's not, no, is it hyperbolic tangent? It's inverse hyperbolic tangent. What is that in terms of ln? I assume Wolfram will tell me. The graph of it doesn't look too bad. Oh, you know, that's actually simpler than I thought. What's the crazy sub? Oh, they probably do the sub in multiple steps. So I've seen the black pen red pen video on integrating the square root of tangent x, and I think it did like 3 or 4 substitutions. But in theory, anytime you do multiple substitutions without doing anything else in between, you can just collapse them all into one big substitution. Anyway, yeah, I glad I didn't spend too much time on that one. In the meantime, let's look for a little question or two off the internet. I really do not know Wish. Oh, or if you're ready critical, I'll look at your stuff, but take your time if you need it. Yeah, I have no idea where this function is even defined, like, or like how it's defined. No, I mean, I'm just filling time, so as soon as you post your question, I'll take a look. Some kind of polar form? Maybe, yeah. I don't really remember. 6 questions? I guess let's take a look. Six aura? I don't know what that means. Oh wait, they said it's E&M, but this is just the motion of a pendulum with gravity. Ah, I feel scammed. 1 Riz point? Okay. Okay. Do you want to post the matrix? This server has had a good amount of traffic, but it's all kind of answered. Oh, this person has to do. Oh, that's a complex integral. Okay, that's a. A complex integral with hyperbolic functions involved. Modified Bessel function of the third, or of the second kind, my bad. Yeah, I don't know how to do that. I respect you a lot, so I'm gonna leave the entirety of that question to you. You are a true friend, Wish. Always giving me, you know, the respect that I really feel I've earned when it comes to Bessel functions of the second kind that I definitely know everything about. You know, do not even bring up Bessel functions of the third kind, you know. Don't even get me started on those. Let's take a look. Oh, wow. You and Oppie? I don't know who that is. I guess I'm gonna go from top to bottom unless you have a preference critical. Bottom? Oh, okay. Yeah, I can do that. Oh, wait. Like Opie and Anthony? I remember like something weird happened with one of them. Cillian Murphy? That name sounds familiar, but I don't know. Oppenheimer? Oh. I might went to a different place. Yeah, you know, that Oppenheimer. Always up to something. Will you 80% understand? Binmox, you're saying yes, it is. Would you make this into a 3x3 matrix and make sure they're not independent? That's what you would want? Oh, and you just found the linear combination that does it. Spanned? So the span of vectors. Oh, you might be able to do the cross product. Well, I don't know. The idea of a vector span. Well, okay. Usually, you are usually given a set of vectors, and you talk about when you talk about the span. You're interested in like what kind of reach does any combination of those vectors have? Um, in SPQ is using the idea of determinants, which is more like something like what I was thinking. I'm gonna try and take the simplest case possible, which is we have our R2 plane here, and if I just have a vector 2, 1, I can scale this vector, add it to itself, subtract it from itself as many times as I want. I will always be locked onto this line that's parallel to this one vector. And you can even give me a whole set of vectors like 2, 1, 4, 2, -2, -1. But all three of these vectors only span this one line because they're all multiples of each other. So 4, 2 is twice of 2, 1. So it's just the same vector, but scaled more. And this is the negative version of... I didn't draw this right. It should be 1, 2. I realize this is a little more towards y, but the idea is the important part. These are all in the same line, so we have 3 vectors here, but they do not span all of R2 because they're all multiples of each other. What you would need is I would say these are not, or these span I think, would you say it spans R1? I'm not really sure of the terminology there, because like I said, my linear algebra isn't that good. But you can definitely say these do not span R2 because there's so much stuff on, all you can do is this one line in R2. You can't do anything off to the side. What you would need are 2 vectors that are called linearly independent. So I'm going to draw 2, 1 properly. It should be more like over here. And you would need something that is specifically not on this line that's parallel to 2, 1. So I'll take like a -1, 3, let's say. You can take now combinations of both these vectors and get anywhere you want in R2. So if I take 2 of these 2, 1 vectors and I take a -1, 3, I can get like up there. Whereas before with like just that one, if I only had like just this one vector here, I can never get up to that point. So it's based on this idea that you can travel along these vectors in multiples and combinations of them. So I would say these do not span R2. I would say 2, 1, -1, 3. Do span R2. And the idea for 3 dimensions is the exact same, except instead of lines, you can have planes as well. So that's like physically what they mean, or like, I guess visually what they mean with what vectors span. And hey, Muhammad Turkman, welcome back. Joseph, well, sleep was good too. Yeah, I mean, you have to span something. You don't say they just span. They do not span R2. They can span something else maybe, but you always want to say they span something. It doesn't make sense to just say the word span. And as Fenlock says, called like the canonical vectors or the unit vector or something. But like 1, 0 and 0, 1 are the simplest examples of vectors that do span R2. And you can actually think of them just like our normal coordinate system. Because if you have just your good old xy plane and you want to plot the point 2, 2, you could think of it as like traveling 2 along the x, so 1, 0, 1, 0, and 2 along the y, 0, 1, 0, 1. Do an n-dimensional casing, some matrix. Oh yeah, so this is a really basic example where you can tell visually whether vectors span, in this case, R2. But as Milk says, like, linear algebra, you're expected to answer questions about arbitrary spaces. So it's not always easy to take 4-dimensional vectors and figure out, you know, you can't really draw a 4-dimensional graph and figure out what kind of shape you might have. So we need some kind of math techniques to do it without having to draw a picture. And that's where we can do a problem like what you posted. Yeah, Fenbox answered it. R2 is 2-dimensional space, so your normal xy plane. Basically, the number is the number of dimensions. Hey, Central. So, like, R1 would just be your good old-fashioned number line. R2 are your xy planes. XY, I'll say that's just X, why not? R3, you have a 3-dimensional XYZ. So every time you're adding on a new axis, I'm not going to draw R4 because I don't know how, but good old 69th, yeah, nice. Oh, thanks for watching via YouTube too, Joseph. But yeah, the R means all real numbers, and the number means how many dimensions you have. And so we're saying it's all real numbers because it's important to talk about. I mean, theoretically, you always want to say what set of numbers you're working with. And in the concept of linear algebra, as far as I know, you always work with all real numbers, so that R is going to come up a lot. You don't really talk about like integers or rationals or irrationals, as far as I know. Just a sexy name. I have a feeling you might be biased there. So to answer your question more mathematically, or the question you actually posted there, critical. The vector u is 0, 4, 4. In the matrix A, 3, minus 2, 1. Negative 5, 6, 1. Right, so the rule with this to remember is you need n many linearly independent vectors to span Rn. So what this means is if you want to span R3, you need 3 vectors. Not just any 3 vectors, though. You have to make sure they're linearly dependent, which means they can't all be on the same line, and they can't all be in the same plane. And similarly for R2, you need 2 vectors. For R4, you need 4 vectors, and so on like that. Hey, Renga. Oh, and I see, why did I write that over on YouTube? Is a circle 1-dimensional or 2-dimensional? I think it's a matter of perspective. Why did I write that, as far as I know? For most purposes, you consider it 2-dimensional, but you could probably have some kind of, you know, if someone like lived right on the edge of that circle, they'd live in a 1-dimensional world from their perspective. They can only go forward or back. So I don't have a very good answer beyond that, but that's kind of my perspective. Renga, this question is from Critical Thinking in chat. About whether this vector u is inside the span of the columns of A here. Oh wait, they give us the graph. Oh, no. Never mind, they give us 2 possible options for u here. U is a constant, A is coefficient matrix. It's not going to be that. What we want to check is whether U is, it's like the example with like U being flat with the plane here means that these are linearly dependent. 1 times 3, 3 times 2? We're not going to be doing multiplication. The trick that we can use here is they give it to us as a 3x2 matrix and a 3x1 vector, but we don't have to keep it like that. We can name a new matrix that is all 3 of these columns and check what the columns span. So this right here is U, this right here is A. And so now we want to row, well, there's 2 different ways you can go about this. You can either row reduce it and see if you get a free variable, or you can get the determinant and see if it's 0 or not. And so we've had suggestions for both. I think Fenbox kind of gave the row reduction solution at the end, and SPQ gave the determinant solution. But there's many different ways that you can solve this. So I think it's you doing more row reduction, so we can just reduce this thing and see what we get. Repeat that. You can solve it either one row reduction, two determinants. Linear algebra, many of the ideas are very interrelated, where getting to one thing implies something about another concept. So there's often like multiple ways to think about things that, as far as I've seen. Yeah, and Rengar was even giving a third, like I would kind of almost call it row reduction, but you could also look for linear combinations. Actually, that's more like what Fembox did before. And basically for linear combinations, you would figure out if the linear combination of these columns, which means each column is a vector times a scalar, and you add them together. That's the same exact thing as what we were talking about before when I drew the planes with R2 and whether they span it. I was taking linear combinations when I was scaling the vectors and adding them. This is the math way of showing that. And you basically do guessing and checking for values of A and B to figure out if you can use these two vectors to make 0, 4, 4. That's like the third way of doing it. But you have to have pretty good intuition with numbers to be able to do this, and even then they can throw some tricky things at you. So this is only really viable, I would say, with simple enough numbers in your columns, which we do have here. The way that I think is more in line with what you've been doing is to do the first thing I wrote, which is row reduction. And actually, oh no, never mind. Let's swap these two rows, I guess. Yeah, I like interchanging first, and then I want to get that one to be a 0, so I'm going to subtract off row 1. I shouldn't go that close to my other work. All right, so we're taking 1 minus -2 is 3. 1 minus 6 is -5. See, and we already get the same exact row here and here. So without even doing any other work, or with only doing a little bit more work, I'm going to take the row 3 and subtract off row 2. Because I just noticed we have 3, -5, 3, -5. 0, 3, -5, 0, 0, 0. That row on the bottom of all zeros tells me that these things are not linearly independent, which means if they're not linearly independent, there's no way these things span all of R3, which means you must lie somewhere in the plane with the other two vectors. And you could have rephrased it as like these two vectors make a plane that this vector also lies in. Like the order of this isn't actually important, but they all three either lie in the same plane or in the same line, and that's enough already to tell us that what the answer to the question is. Yeah, so you could continue reducing that, and I would, you know, divide something by 3, divide something by 4, but it's unnecessary. A unit circle could be one-dimensional. Oh, interesting perspective there, Joseph. Oh, they don't have to, yeah, that, for as far as pivots, I don't really know what the term actually means, so. Well, so here's the thing. We wouldn't say infinitely many solutions because we were never equal to anything. There's no like equation to have a solution for. But if it was equal to something, there's infinitely many solutions like at play potentially, or there just are. What we would say is these vectors are not, well, it depends on what you're equal to, whether it's infinitely many or no solutions, but what I would say is that these vectors are not linearly independent, which means they do not span R3. Hence, U must lie in the same plane as the columns of A. Something like that. I think it's the same thing that Fenbox came up with that Renga put. Right. The vectors not being linearly dependent is the most important takeaway from this problem. Well, and also that geometrically that implies they're all in the same plane. Those were probably the two important things there. So we have this case on the bottom here where U is inside this blue plane, rather than U pointing up away from the plane. Hey, Mailman Joe, welcome in. So yeah, that would make sense. Critical. Thanks for the follow as well. Welcome in. I didn't say that. I think I did say that. But you can have two welcomes also. Glad to hear it. So A is the matrix they give you. X is a generic vector. Yeah, a variable vector is maybe a better way of saying it. I'll show you the metaphor for this type of problem with a system of equations, because you've definitely seen those before. Oh, who's that? Oh, Ben. Thank you so much for the raid, Ben. Well, welcome in, everyone. How's your stream? You're doing X Defiant? Hope it went well. Being math for too long, you're starting to see things in the corner of your vision. Yeah, Joe. We're just working on some linear algebra problems from Critical. Start and then switch to X Defiant. Oh, good. Yeah, so this is it's almost great stuff that you're doing, Ben, but it's like I'm still having the struggles where I like only half remember your algebra. I'll show what AX means up on the board here. You done with that? Yeah. I mean, you probably have to do more if you get into pure math, but I don't know. I guess it depends on the type of pure math. I'll be able to get some credit. Oh, yeah, fair. All right, so we said that A is 2, -1, -6, 3. B is B1, B2. Well, A is the matrix that they give us, that 2x2 matrix. They don't tell us what X actually is, but we, besides X is a vector, but we can kind of fill in the blanks that when they say the vector X, they mean some generic vector x1, x2, or depending, your class might be using X and Y. These are the exact same thing. So if you have AX, and I'm writing arrow because you can't do bold text, you know, in writing, but bold X and X with an arrow are the same thing. It's talking about matrix multiplication. Are you using X and Y or X1 and X2? I assume you're using X1, X2 if B1, B2 looks like that. But AX means literally doing this 2x2 matrix times that 2x1 matrix. X1, X2? Okay. And so, and they're saying that AX equals B. And I want to show you that this is the exact same thing as a system of equations. Because when you do the matrix multiplication here, what you do is you take 2 times x1 plus -1 times x2. Sorry, I should lead off with saying the rule of how I was taught it is that this is a 2x2 matrix, this is a 2x1 matrix, and because these twos match, like the dimensions on the inside are the same, you're allowed to do matrix multiplication, and your result is a 2x1. It's a nice little like a aesthetically pleasing pattern to me. So if you take a 2 by 2 matrix, multiply a 2 by 1 matrix, your result is a 2 by 1 matrix. The first row in that 2 by 1 matrix is 2 times x1 plus -1 times x2. The second row is -6 times x1 plus 3 times x2. And it's still equal to b1, b2. Thanks for the work, Fenbox. And if we just ignore the matrix stuff for a minute, this is the exact same thing as a system of two equations. Like, if I separately gave you the problem 2x plus 3y equals 5 and x minus y equals 2, I bet you can solve that. And this is the same exact thing, just we have b's instead. And that means this thing up here is the exact same thing as a system of equations like that. Like, linear algebra provides a more systematic way to do this same calculation. And it's really important for higher dimensional things where you have way more rows and way more columns, and it gets a lot more complicated. But that's basically like what this question is asking is, when does a system like that have a solution? When does it not? Because if you remember from a problem like that, you know, we could get 0 equals 2, which means there's no solution. We could get 0 equals 0, which means there's infinitely many. Or we could get x equals 1, y equals 2 or something, which means there's one solution. Same thing could happen with the matrix stuff. And so they're asking, when does this system have no solution, and when does it have a solution? So when you have an equation like this, we often use augmented matrices as an abbreviation for basically solving that system of equations, where you take your matrix A, 2 minus 1 minus 6, 3, you do a vertical bar, and whatever you're equal to, b1, b2. And the generic x vector is implied. Like, we don't really care about it. Because these are things that actually affect the solutions. So I would row reduce this and look for a solution to this system. And because I've done these a lot, I can tell right off the bat that this row is 3 times that row, -3 times that row. So let's add 3 times R1. Two minus 1, B1. -6 plus 3 times 2 is 0. 3 plus 3 times -1 is 0. B2 plus 3 times B1 is just B2 plus 3B1. So we have a row of zeros here. That means we either have no solutions or infinitely many solutions. And the question is, when is it which scenario? Like, for what b's do we get what? Well, not necessarily infinite. Remember, like, over in the system of equations thing, if you get 0 equals 2, it's a false statement. There's no solutions in that system. If you get 0 equals 0, that's always true. There's infinitely many. So we could actually write this as a system of equations like we did over there, kind of. So 2x1 minus x2 equals b1. 0x1 plus 0x2, you can just call it 0. So b2 plus 3b1. Now this equation on the second one is the important one because it has the zeros. This statement here, we have to figure out when it's true and when it's not true. So if b2 plus 3b1 is equal to 0, this is a true statement, and there's infinitely many. If b2 plus 3b1 is not 0, it's not a true statement, so we have no solutions. So it depends on what your b is. Yeah, like what you're saying in chat, critical. So, I wonder how you would express this. I would say, let's just solve this for b2 arbitrarily. We could solve it for b1 as well. But we can say that b2 is equal to minus 3 times b1. So if this condition is met, that, you know, b2 is negative 3 times whatever b1 was, we have infinitely many. And we have none if the opposite is true, if it's not equal to that. And I might write it instead with a free variable. So if b1 is equal to t, then there are infinitely many solutions if b equals, well, we don't even need this first statement. If b equals, you know, t, whatever your b1 is, and negative 3 times t. That's called like parameterizing or something like that. We have infinitely solutions. You often like can name your free variable, and I'm just naming it t. So whatever our b1 is, we want to make sure our b2 is negative 3 times that, basically. And I would say, and no solutions otherwise. That's basically the answer that I would put there. Yeah, Renga. I'll bring the question up right now. The columns are linearly dependent. The image of the span, the range is one-dimensional, so you need to find the spanning vector. Yeah, I mean, that's kind of the 200 IQ explanation that SPK put, at least for the start there, but yeah, when SPK says by looking, that's kind of something that you have to build as you do more of these. Like right as I looked at this problem, I noticed that 2 negative 1 times negative 3 is the bottom row. And relating back to that last problem, if we look at the vectors that the rows form, one, two, 1, 2, 3. 2, 3. Okay, so 2, -1 is that vector there. -6, 3 is that vector right there. If my drawing skills were better, you'd see these are in a perfect line. And so they do not span R2. They're literally dependent. Sorry, I just heard some weird noise. So any solution to this system of equations has to be on the same line. Otherwise, there's no solutions. And this is an expression of that. I think critical's decently early on into their linear algebra class. I'm not sure. I was right in using rows, right? Or does it make a difference with columns versus rows? The columns certainly aren't independent either. Right, the issue is the matrix A does not span R2, which means that for any given vector, there's either no solutions or infinitely many solutions. It is always like that if that condition is met. Often they'll give you an actual B to work with, but yeah. Is 17... What is the matrix A here? Okay. How many rows matrix A contain a pivot position? I don't know this one. I'll look up what a pivot is.
We have to row reduce A first. I think is the issue. But yeah, after reducing, I think I saw you going back and forth with Megalomorph, and Megalomorph was being pretty helpful about that. So, and you already know like how to look for a pivot. So yeah, I would take A then. Okay, great. I would take A, row reduce it. You don't need to get it. Like you don't need to care about getting the first entries to be 1. You can save yourself that amount of work, but you need to get like that lower triangle of zeros or whatever it happens to be. And count your pivots then, because this thing is not reduced. It's either echelon form or row echelon form. I don't know. The site I was just looking at calls it just row echelon form. Like that 4 is allowed to exist, whereas reduced row echelon form, that would have to be a 1. If you do well in your credit exams, linear algebra, differential equations, Calc 3 will be your second term. I think row echelon form and echelon form mean the same thing according to this Google search, or at least echelon form isn't bringing up anything unique. So we might be saying the same thing with, well, okay. The way that I learned it and the way that websites seem to be talking about it are there's row echelon form and there's reduced row echelon form. You might be using echelon and reduced echelon to mean the same thing. Okay. For what it's worth, Joseph, I wasn't a fan of linear algebra personally, but differential equations and Calc 3 are pretty fun to me. Of course, everyone's like preferences vary, but and some people love linear algebra as well. Column echelon form? Oh, okay. Interesting, SPQ. I think this capital B matrix, is it for another question? I don't think it's relevant to question 17. Transpose of row echelon. Oh, I guess that makes sense. So I think, yeah, so I think this has become, oh, okay. So I'd rather you do this. I think it'll be more instructive. I think you need to row reduce A. Yeah, please do. And then you need to do the same thing as we just did in the last problem. Because it's the exact same thing. They're giving you a generic B vector. Oh, no. Oh, wait. My mic is still on? I'm pretty sure I'm still coming through. Hey, Sergio Lopez. And hey, Bluebird, operations you can instrument column operations. Okay, yeah, I feel like I've heard that like a lot of things you do with rows you can do with columns too. I don't know what the rules are because I was never taught it. I think like Penn Center has talked about it. Thanks for confirming, Joseph, as well. Can you hear again? Okay, cool. So I hope I've given you enough to do 17. I'll even like type it out here. B vectors have a solution. So let's look at 21. Okay, so for 21, whenever I see these problems at first, I'm good enough with it that, or, I've seen these problems, just enough that I can do some mental math and try multiplying and scaling columns and adding and subtracting them to get a feel for whether I think it's independent or not. And as far as I can tell, I can't use any of these two vectors to make the third vector. So I'm thinking these should be independent because I can't find any linear combination of two to make the third. But we should probably go to row operations to show it in a way that you're more familiar with. Oh, that's an interesting way of framing it, SPQ, yeah. Or not? I feel like that there's an idea there. Can you answer this while doing any calculation you were saying conceptually? Yeah, Rangoff, you have another perspective. Please share, because my instinct is just to still resort to row operations here. I mean, there's a little, like these middle two ones are the ones that I'm looking at, because like this negative one is unique. Oh, wait. Oh, R4. You're right. I was thinking of R3. I was making these three-dimensional for some stupid reason. I'm sorry. I misread this. I would go back to the rule that I said before. You need n many linearly independent vectors to span Rn. Here we have R4, which means we need 4 vectors. We only have 3 vectors. There's not a shot in hell that this spans R4. You need 4. So off the bat, we can just say these do not span R4 without having to do any calculations. These 3 vectors do not span R4, and that's the reason, because we only have 3. How do you do the all real numbers are in LaTeX? Independent to span. Thank you, Renga. I want to type out this rule for critical. So I think it's a bit easier to like read it. Oh, independent. That's a terrible typo to make. So because of this rule that I wrote on the board earlier that I typed here in chat now. Oh, really? lowercase b worked. What does capital B do? One second, I'm gonna do a little test because I'm curious. Capital B did not. Are these even case sensitive? No worries. I'm pretty terrible with LaTeX. Yeah. This was the same thing as I wrote on the board earlier. We have R4, or they're asking about R4, which means we need 4 vectors. If we only have 3 vectors, we can immediately shut the door. There's no way we're spanning R4. And I think it's as simple as, or that's the quickest solution for this one. Bluebird, you could span R4 with I mean, you can have something in R4, like a line, a plane, or whatever an R3 shape is. A cube? I don't know. Like maybe that could exist in R4, but it's still a 3-dimensional shape. Is that the... Oh! You're saying if we had like 5 or 6 vectors. Sure, yeah. Yeah, critical. We would need one more vector matrix. It's the same, we can think of the same thing in this context. I'm thinking about their question you just typed there. So yes, you can be given more than 4 vectors and span R4. The extra vectors are, you're going to have some type of linear dependence, but how does that work? So if you have, you are only guaranteed to have 4 linearly independent vectors at most, but the extra vectors, there's always gonna be some kind of like dependence. I'm not explaining it well. Yeah, if you have more than 4 vectors, it gets a little murky. You have to do some row reduction to check what they actually span. Because you have to check what's linearly independent. Okay, yeah, so if you're given, say, 5 vectors, you could span R4, but you could also span R3, R2, R1 instead, and that depends how related those columns are. So you still need to do some row reduction work. I think maybe making this exact question a little bit too complicated, but Bluebird is right. So it's possible they throw a curveball at you where they give you 5 vectors and ask if they span R4. But you can, the procedure of like doing row reduction will still work. What I want to say probably is you perform operations columns. It's like multiplying A on the right. Huh. Okay. Yeah, exactly. Critical. If you had, say, 5 vectors, you could end up with just a column of all zeros, in which case you kind of exclude it. And you are left with 4 linearly independent vectors that you know then span R4. It's also possible to get, 2 or 3 or 4 columns of zeros, in which case your span is even less. And that's the thing that you have to check for. But yeah, if you have 5 vectors, you will always have 1 vector that ends up being 0. At least 1, I should say. It's a better way. As of both these or just 1? Just 47? So the columns span R4. Is there a thing that says column span is the same thing as row span, or how do you do this? Or do you just transpose it and do your normal stuff? Let's reduce, but do we have to transpose it, Rengar, or can we just take the matrix at face value? I feel like if something like the rank is equal to whatever the equivalent of rank is for columns, and that's why you can just column rank and row rank are the same. Okay, yes. That's the thing I was thinking that SPQ said. All right. So Critical, I think the message here is that I assume this is somewhere in your book or notes, but the number of linearly independent vectors is the same for columns and rows. So I would just take this matrix, reduce it, and look at how many independent rows you have. And the answer for columns is the exact same. A dual operator on dual space? I don't know what that means either. Independent or dependent? Here, I'll type this out for you as well. Matrix as normal and determine how many linearly independent rows there are as normal. The number of linearly independent columns is the same. You have 4 linearly independent columns. You span R4. Um, that's kind of a weird thing, but there's a relationship between the number of independent rows and columns. So we can really treat this as like they're asking about the rows in a sense. As for the purposes of this question, there probably is some like subtlety in a different type of question maybe, but does this like procedure make sense to you? They don't? I'm not going to do the work of reducing this, but we can make Wolfram Alpha do the work of reducing this. The answer is they don't span R4. It means there's no independent row. It means you should have a row of zeros, if that's what you mean. I don't really mean with no independent row. It means there's at least one row of zeros, though. So if that's what you're thinking in your head, then I agree. What is this? Diagonalizations. Okay. Why don't they give me RAF? There we go. Okay, yeah. Wow, what a beast. You don't have to get into, you can get into just row echelon. Does Wolfram Alpha know how to do that? Nope. You don't have to go full reduced row echelon form. Like, you don't have to get all the ones there. But you should try to get a row of zeros on the bottom, and then you're done. Yeah. You don't have to get multiple. As soon as you get one, you have the answer to the question. And this one, there aren't multiple, but in theory, in other questions, that there could be multiple rows of zeros, but you don't have to care about that. Yeah, does that mean that you're all settled these questions, at least for now? Awesome. Glad to hear it. Yeah, no worries. um... I'm just debating what I want to do right now. I I haven't beaten Elden Ring. I've been playing it for like at least a year off stream, but I've been making progress really slow. Level 1 run? No, I never done a challenge run in a Souls game. I haven't been as big a fan of Elden Ring as I have been of other Souls games. Yeah, no, I mean to finish it at some point. I'm a huge fan of Souls games, but Elden Ring in particular, I'm not as big a fan of. Um, I think I am gonna call it for the day because my throat's not feeling too good. I should give my voice a rest. Yeah. So I'm gonna end the YouTube stream. Hey, Fembox. You caught me right about to call it. Sorry. So it's time for the end, yeah. So anyways here on YouTube, I appreciate you. I'm back on YouTube on Tuesday.